students, I welcome you for the today's lecture related to the response of the impulse system and the sinusoidal input. We have already discussed the different forcing functions, that is the step forcing function, ramp forcing function, sinusoidal forcing function and the impulse forcing function. Now we will discuss the response, that is the output, how you will get the output for the step change or for the impulse or for the sinusoidal input. Now we will discuss the impulse response equation. So this impulse response equation, that is the input variable is xt. So where A is the magnitude of the impulse change and A is not the function of time. So this is what our impulse forcing function that is there. For time t is equal to 0, the value is x. A sudden change is observed and again its value reduces back to its original position. This is both the values are at time. Delta t is very small. Delta t change to 0 and this is of a magnitude a. So xt, which is equal to the a. But for small delta t tends to 0, my value of the Laplace transform xs, which is equal to the a. So writing the transfer function for the first order system, that is gs, which is equal to ys upon xs, which is equal to 1 upon 1 plus tau s. Now substituting the value of xs as a, you will get ys, which is equal to a upon tau upon s plus 1 upon tau. Here the tau that has been taken out, so this becomes s and plus 1 upon tau. So this is 1 upon tau. So that taking the inverse Laplace transform of this, you will get a upon tau e raised to minus t upon tau. So this is the impulse response equation, that is the yt, which is equal to a upon tau e raised to minus t upon tau. How this is simplified? Simple by substitution and by simplification. Sometimes you require partial fractions for simplification, then your values of c1, c2, c3 they are calculated, and then you will take the inverse Laplace transform, and after that you will get the final yt as the response, as the output equation. This yt is nothing but the output of the response equation. Now I am going to plot a graph for this. So at yt upon a against t upon tau, yt tau, ये वैल्यू पूरी इस साइड में लेकर आई, so that yt tau upon a versus t upon tau that has been plotted. So for this it is equals to the 1 and then this value goes on decreasing. So this value, you will see the graph. So if you will plot these values for different values of t upon tau 1, 2, 0, 1, 2, 3, 4, 5, 6, against this yt upon yt tau upon a, yt tau upon a. So for different values of the t upon tau, these values are plotted. So you will get, observe this value decreasing graph that has been observed. There is a second way also to obtain this thing. The differentiating the step response equation results the impulse response equation. Differentiating the step response equation results the impulse response equation. So what is step response equation? Yt for the step response equation is a into bracket 1 minus e raised to minus t upon tau. So after differentiation, you will get the dyt upon dt at step a upon tau e raised to minus t upon tau, which is nothing but same as this. So this is nothing but the differential of the first order step response equation will give you the output for the impulse response equation, because it is for a small time change. Delta t is very small, that is what you can differentiate it. Now the fourth stage, that is the sinusoidal response equation. Consider this, the first order system subjected to a sinusoidal change. Now what is the sinusoidal change that we have already discussed? That will get a constant value, amplitudes are same, a is same. So this is the a sine omega t. That is what? The input signal that is there. A xt, which is equal to a sine omega t. So taking Laplace transform for this, which is xs, a omega upon s square plus omega square, substituting this ys transfer function for the first order system, ys upon xs, which is equal to 1 upon tau s plus 1, substituting the value of xs from here and doing the simplification by partial fraction method, substituting the cross multiplying, substituting the value of s, which is equal to 1 upon t, calculate the values of c1, calculate the values of c2 and c3, and finally you will get the equation ys as this, and the yt equals to this. Now again this can be simplified so that the final form the simplification for use is this. So this is the response equation for the sinusoidal forcing function. You can go through this derivation also. Yt, which is equal to a omega tau upon 1 plus omega tau square e raised to minus t upon tau plus a upon root of 1 plus omega tau square sine of omega tau plus theta. Now if you substitute the t tends to infinity, that means at a steady state, what will happen? At a steady state, what is going to happen? So substitute the value of t upon tau, that is equals to the infinity, so this will become the 0, and your value that will only obtain yt at steady state, this will be only this function, a upon root of 1 plus omega tau square sine omega t plus theta. Now what is the amplitude ratio? Amplitude ratio is nothing but the input amplitude to the output, output amplitude to the input amplitude. The ratio of the output or the response amplitude of variation to the input amplitude of variation, that is called the amplitude ratio. Output upon input is the ratio that has been taken into account. So xt which is equal to the A sin omega t. That is what? The input amplitude ratio. And the output amplitude ratio is A upon root of 1 plus omega tau square into sin omega t plus theta. This is the output amplitude ratio. तो इसका ratio लेने का है मेरे को. So the input amplitude क्या होगी? A is my input amplitude. And output amplitude is A upon root of 1 plus omega tau square. So input amplitude is A, output amplitude is A upon root of 1 plus omega tau square. So therefore amplitude ratio is 1 upon root of 1 plus omega tau square. Now if you are going to plot or write it in terms of a graphical representation, the bold line that indicates the input, the bold line that is related to the input, and this dotted line that is related to the output. So this is what the input xt, input variable, and the output variable yt, that is plotted against this phase lag, plotted against the time t, plotted against the time t. So this is what a sinusoidal wave that has been achieved with an amplitude A. But the output amplitude is A upon root of 1 plus omega tau square. This is what? The output amplitude. And there is a lag which is also observed for this peak and for this peak. The input का peak जो है वो और output का peak जो है वो, उसमें phase lag आ रहा है. That is what the time lag that has been observed, and this is the phase lag written in terms of a phase lag. So this is the amplitude ratio that is given as 1 upon root of 1 plus omega tau square, and therefore it is always less than the 1. That is why it is always less than the 1. The ratio is less than the 1. Then the phase lag theta, that is tan inverse of minus omega t, and the output response is lagging behind the input by the time, which is given as theta upon 360f. This is the lagging. How much time the output response that is lagging behind the input. Input पहले होगा और उसके पीछे पीछे output चलेगा. So this is related to the derivations or the inputs for the first order system with the four forcing functions. Now we will see the different numericals related to this. So the first numerical that is related to the step change. So we can consider the four numericals, but that is one related to the step change, one related to the ramp change, one related to the impulse change, and one related to the sinusoidal change. So one by one we will see these numericals. Now the numerical that can be same, a thermometer. A very common example, you can also imagine that. A thermometer having the first order dynamics with the time constant of the 6 seconds and is placed in a temperature bath at 30 degrees Celsius. After the thermometer reaches a steady state, that means it has attained a 30 degrees Celsius value. It is suddenly placed into the hot fluid at 60 degrees Celsius. That means initially the thermometer is there, which is having the temperature of 30 degrees Celsius, and then it has increased or put suddenly into the temperature where its temperature is exposed to the 60 degrees Celsius. Here the temperature is 60 degrees Celsius. Initially the temperature that is 30 degrees Celsius. But what is the change we have to observe? The output is, this is what is the output expected, 60 degrees. But initially वो 30 डिग्रीज है. इसको मैं ग्राफिकली जब ड्रॉ करूंगा तो इनिशियली दिस वैल्यू इज एट 30 डिग्री सेल्सियस, राइट. एक्स इनिशियल टेम्परेचर 30 डिग्रीज है. स्टेप चेंज ऑब्जर्व हो रहा है, दैट इज व्हाट द मैग्नीट्यूड ए विल बी इज इक्वल टू द y माइनस एक्स. तो ये वैल्यू जो है ये 60 डिग्रीज वैल्यू है. This value is 30 degrees. So this value is 30 degrees. This value is 60 degrees. So magnitude is nothing but this step change. So magnitude M is 30 degrees Celsius. Then the steady state temperature initially at 30 degrees Celsius. Final step change is 60 degrees Celsius. Now our step response equation is yt, which is equal to the mk into bracket 1 minus e raised to minus t upon tau. Now this is the k, steady state gain for this thermometer, that is 1. So only your equation reduces to m into bracket 1 minus e raised to minus t upon tau, where yt, which is equal to the yt minus ys. This ys is the small ys, and it is having the value of 30 degrees Celsius. Initial value कितनी थी उसकी? 30 degrees थी. जो कुछ रिस्पॉन्स मिल रहा है वो 30 डिग्री के ऊपर मिल रहा है, that is why I have to add this 30 degrees, initial 30 degrees. 30 डिग्रीज के बाद में उसका टेम्परेचर बढ़ने वाला है 30, 40, 45, 55, 60 डिग्री ऐसे बढ़ेगा, ना ही जीरो से बढ़ेगा. If you will do calculation with the zero, then I have to add to the 30 degrees. I can afterwards add this 30 degrees also, that can serve the purpose by simply considering this yt value. Only the change values, this yt is going to give the change value. That is why we call it a Laplace transform of the output deviation variable. Deviation is the change, initial value minus final value, final value minus the initial value. That is what the change that is concerned, and that is why we are observing or we are adding this 30 degree initial value here. So at time t is equal to 3 seconds, so yt, which is going to give me the 41.8 degrees Celsius, I can substitute the different values for t and can do the calculation for time t is equal to 6 seconds. Yt, that comes as the 48.96 degrees Celsius. Then for t is equal to 10 seconds, yt comes out as the 54.33 degrees Celsius. So similarly, these calculations that can be done for the thermometer with a step change. Now the second equation, second example, that is related to the impulse change. Same thermometer that is there, example. A thermometer is observed to exhibit the first order dynamics, is having the time constant of 6 seconds and is placed in a bath. The bath is subjected to the impulse change of magnitude 3 degrees Celsius. The steady state temperature indicated by the thermometer is initially 30 degrees Celsius. Calculate the temperature indicated by the thermometer at t is equal to 3, t is equal to 6 and t is equal to 18 seconds. Now, what is happening in this example? That is, initially the thermometer is at 30 degrees Celsius and the temperature is increased at a constant rate, that is of magnitude 3 degrees Celsius. Initially the temperature is at 30 degrees Celsius. initially 30 degrees Celsius. So yt, which is equal to a tau e raised to minus t upon tau, that is my response equation for the impulse change. And the magnitude of impulse change is 3 degrees Celsius. Magnitude of the impulse change is 3 degrees Celsius. This is what? 3 degrees Celsius. Magnitude of impulse 3 degrees Celsius that has been changed. So A is the magnitude of impulse change, which is 3 degrees Celsius, and initially its temperature, that is 30 degrees Celsius, that has been added. So yt, which is equal to ys plus a upon tau e raised to minus t upon tau. So you can substitute the value of a, that is the 3 degrees Celsius, and the time constant as the 6. So time t is equal to 3. I can note down the temperature that comes as the 30.303. Then 30.18, and then after 80 seconds it comes as the 30.025. So you can note down the time constant is 6 in this case. So initially at 3 seconds it has increased. So this is what my input that is observed, small change that is noted down. But what is the output I will get now? The temperature initially, that is 30 degrees Celsius, and this magnitude that is of 33, you can say then 30 plus 3, initially 30 degrees Celsius है, ये 33 degrees Celsius है. Magnitude is A is 3 degrees Celsius. So how the temperature that is going to increase? The initial time में जो कुछ है वो 30.3 तक जा रहा है, 30.3 तक जा रहा है, then it decreases and will attains in a certain time constant. So temperature पहले increase हो रहा है, then slightly decrease हो रहा है, then again decreases after certain time. So this is related to the response of the impulse forcing function. Now the third example that is related to the sinusoidal forcing function. A thermometer is observed to exhibit the first order dynamics. The response of the thermometer was evaluated by applying a step change in the bath in which the thermometer is placed. After 6 seconds, the output value was 63.2% of the total applied step change. The thermometer reading at temperature of 55 degrees Celsius was put into a bath whose temperature was varied sinusoidally between 50 degrees Celsius and 60 degrees Celsius with a 60 seconds per cycle period of oscillation. Now thermometer that is initially placed, the temperature reading at the thermometer reading at the temperature of 55 degrees Celsius. Initially it was at 55 degrees Celsius and was put into the bath whose temperature was varied sinusoidally for 50 degrees Celsius and 60 degrees Celsius. So I can plot a graph for this. Initially it is at 55 degrees Celsius. Initially at 55 degrees Celsius. Then at certain time t equals to 0, it started deviation of say 60 degrees, and then it goes 5 degrees 0, that is at 50 degrees. Then it again goes to the 60 degrees, then it goes to the 50 degrees, and that is what this cyclical phenomena that is being observed. So this is the amplitude is plus minus 5 degrees is the amplitude, right? So after 6 seconds, the output value was 63.2% of the applied step change. So output amplitude, that is nothing but the A upon 1 plus omega tau square sine of omega t plus theta, where theta is the phase angle, what is tan inverse of minus omega t. The input amplitude variation A is the 5 degrees Celsius. That means it is fluctuating from 55 degrees Celsius to 50 degrees Celsius and 60 degrees Celsius, plus minus 5 degrees. So that is what the amplitude. The output amplitude variation is A upon 1 plus omega tau square. Now omega, that is in radian frequency. So here omega, which is equal to 2 pi f, and t is the period of oscillation, which is 1 upon f, that is the cyclic frequency. So your cyclic frequency that is mentioned is the 60 seconds in a cycle. 60 seconds per cycle. 60 seconds per cycle that has been mentioned. So omega, that comes as the 1.04 radians per second, and you can calculate the response of the first order control system, that becomes 63.2% of the actual value, the applied magnitude. So t upon tau, that comes as the 1. So the time constant, that is 6 seconds. So amplitude ratio, which is equal to 1 upon root of 1 plus omega tau square, you can substitute the values. The output amplitude variation, that comes as the 4.24 degrees Celsius. So input amplitude is plus minus 5 degrees Celsius. The output amplitude is 4.24 degrees Celsius. There is a difference. So maximum temperature that is achieved is the 59.24 degrees Celsius, and the minimum temperature achieved is the 50.76 degrees Celsius. So what will be its graph then? So graphically, if it is represented, if it is at a 55 degrees Celsius temperature, that is there, this is at a 55 degrees Celsius. My sinusoidal input, that is, this is what? The input that is there with an amplitude of 5 degrees Celsius that will exist. So this amplitude is of a 5 degrees Celsius. This is 5 degrees Celsius amplitude. Now what is happening to the output values? That we will draw. It will start after certain phase lag. This will be my output with a certain phase lag and with a lesser amplitude. But here the amplitude that is there, which is 4.24 59.24 degrees Celsius. The maximum value, the minimum value of this, that is this 50.76, and this value of 59.24 degrees Celsius is the maximum value, this value, as well as this value, both the values that can be 59.24 degrees Celsius. So this is related to the response what you get in the first order system and its numeric.